9. Today we are taking a look at properties of radicals. And if you remember from earlier on this year, we looked at radical expressions and we learned to write radical expressions as fractional or rational exponents. Well, today we're taking a look at properties of radicals. So a few terminology things. A radical expression, first of all, is just one that contains a radical. That's that little kind of check mark symbol. Where n is known as the index number and x is called the radicand. That's the number underneath that radical symbol. All right, so for example, the square root of 5, our index number here, 2, is not written. Whenever we're taking the square root, we don't need an index number. We have the cube root of 27, and so our index number there is 3, and our radicand is 27. Or we have the fourth root of 16, our index number is 4, our radicand is 16. So radicals have properties just like exponents do. Our first property that we're taking a look at is called the product property, and it says the root of a product is equal to the product of the roots. In other words, whatever that radicand is can be broken down into some certain factors. So for example, the square root of 45 is not a perfect square, but I can break that down into its product 9 times 5. And I can now take the square root of 9 times the square root of 5. Well, the square root of 9 is a perfect square, so that's going to simplify to 3 times the square root of 5. Another way we write that is without the multiplication symbol there, so it's called 3 root 5. Now, the quotient property, again, this might seem familiar to you. The root of a quotient is simply the quotient of the roots. So, for example, we got the square root of 3/4. That really can be broken down into is the square root of 3 divided by the square root of 4. Now, the square root of 4 is a perfect square, so we can rewrite this as root 3 over 2. All right, in example 1, we want to give the index number, the radicand, and evaluate the radical expressions. So here we have the cube root of 125. So our radicand here, and we're going to abbreviate it, is 125. Our index number is 3, and when we evaluate the cube root of 125, our solution there is 5. All right, next up we got the square root of 144. Our radicand here is 144. That's the number underneath that check mark. The index number is 2, so we're taking the square root of that. The square root of 144, its solution is 12. All right, next up we got the fifth root of negative 32. Radicand is negative 32. Our index number here is 5. Now remember, you can take an odd root of a negative number. So the fifth root of negative 32, the solution there is negative 2. All right, well, taking square roots and cube roots of numbers is easy enough. How about if we add in some expressions now? So for example, the square root of 144x to the 4th. So we can break that down into the square root of 144 times the square root of x to the 4th. Remember that product rule. And we know what the square root of 144 is. That's going to simplify to 12. What about the square root of x to the 4th? So remember, we can break this down further if we'd like. We can take the square root of x squared times the square root of x squared. Now, when we take the square root of something being squared, it just undoes itself. So this is really 12 times x times x. And so our final simplified version here is 12 times x squared. Now, maybe you were able to jump to that right away by evaluating the square root of x to the 4th. Because keep in mind, you could rewrite that as a rational exponent. That's x to the 4 halves, and x to the 4 halves simplifies to x squared. Let's try our next one here. We have the cube root of negative 8. So we're going to break that down. The cube root of negative 8 times the cube root of x to the 12th. So once again, we know the cube root of negative 8 is negative 2. The cube root of x to the 12th can be rewritten as a rational exponent. My power is my numerator. My root is my denominator. So we're going to write that as 12/3, and that simplifies to negative 2 times x to the 4th. All right, for our next example here, we've got the fourth root of 81 times the fourth root of y to the 4th. And so that's going to simplify down to 3y. All right, let's use our quotient property to simplify each expression here. I got the square root of 25 divided by the square root of 36. We know both of those off the top of our head. That simplifies to 5/6. How about the square root of 121 over the square root of x squared? That gives me 11 over x. And then our last one here on this first page is the square root of 4x to the 4th. Make sure that radical goes all the way across. Divided by the square root of 64. That's going to simplify to 2x squared over 8. And you can go one more step. That 2 over 8 will simplify to 1/4 and then x squared. All right, turning the page over now. We have some other types of radicals here that we want to learn to simplify. So this was kind of like our first example on the front page where we had the square root of 45. Well, the square root of 75 is not a perfect square. However, you want to think of factors of the radicand. Remember, that's the number that's underneath that radical. Factors of the radicand that can be simplified, that can be reduced. All right? Now, here's what I mean by that. Since we're taking the square root, what's a perfect square that divides into 75? Well, that's 25. So I can break down 75 as the product of 25 times 3. And therefore, the square root of 75 can be broken down into the product of the square root of 25 times the square root of 3. And the square root of 25 is 5. So my final simplified form here is 5 root 3. We can do the same thing with cube roots. And if I take a look at the cube root of 24, it's not a perfect cube. However, there is a factor of 24 that is a perfect cube, and that's 8. So I can break down 24 into its factors of 8 times 3. And therefore, the cube root of 24 breaks down to the cube root of 8 times the cube root of 3, which is 2 cube root 3. So there's your final simplified form of the cube root of 24. All right, next up we got the fourth root of 48, which I can break down to the fourth root of 16 times the fourth root of 3. The fourth root of 16 is 2, so that's 2 times the fourth root of 3 is its final simplified version. So we can follow these same properties when simplifying expressions with other roots, such as cube roots, fourth roots, etc. Note that cube roots, remember, can have a negative radicand. That number underneath that radical symbol can be negative. All right, let's try simplifying some of these expressions now. We have the cube root of 135. So I want to think of factors that are perfect cubes of and that divide into 135. Well, that is the cube root of 27 times the cube root of 5. Now, if you didn't know that, what you would start doing is taking your calculator and dividing it by perfect cubes. So you would divide it by 8, you would divide it by 27, you could divide it by 64, and so on and so forth until you find some factors that you could reduce 135 by. All right, so we have the cube root of 27, that's 3, and then 3 root 5. So there's our final simplification. Let's take the cube root now of 8, x to the 4th. So let's break this down as to the cube root of 8. And now we're going to take x to the 4th. X to the 4th, well, 4 is not divisible by 3, like some of our previous examples. So what you want to do is you want to think of a number less than 4. All right, what's the highest number less than 4 that's divisible by 3? Well, that number would be 3. So you're going to write this as the cube root of x cubed times the remainder amount, which would be the cube root of x. Because if you were to multiply these back together, you would end up with x to the 4th. So now we can simplify these first two. This becomes 2. The next one is x. But I can't simplify that third term there, so it just remains as the cube root of x. All right, there's your final simplification. let's skip over letter C for right now. Let's go down to letter D. Let's see if we can do something similar. We've got the fourth root of 32, which is going to break down to the fourth root of 16 times the fourth root of 2. And then we have t to the 7th. Well, 7 is not divisible by 4, so you want to think of the number, the highest number less than 7 that's divisible by 4. And that would be 4. So this is going to simplify to the fourth root of t to the 4th times the fourth root of the remaining amount, which is t cubed. All right, so the ones I can simplify are my underlined ones, and the other two I'm going to circle. Those can't be simplified, so they stay as is. The fourth root of 16 is 2. The fourth root of t to the 4th is just t. The other two remain the fourth root, and then we're going to put them back together, of 2t cubed. All right, let's jump to our next example here. This fifth root of 128, p to the 10th, and b to the 8th. So our fifth root, we can start thinking about factors of 128 that might be perfect fifth powers, and it's 32, okay? Now, the remaining amount of that, oops, I did third root there. It's supposed to be fifth root, my bad. So that should be the fifth root of 32 times the fifth root of 4. All right, now we got p to the 10th. We have the fifth root of p to the 10th because 10 is divisible by 5. And then we got the fifth root of b to the 5 and its remaining amount, which would be b to the 3rd. All right, so simplifying, I can simplify these underlined ones here. And then the two circle ones, I can't simplify any further, so those stay as the fifth root. So I end up with 2p squared b times the fifth root of 4b cubed. Whew, this is getting to some big boy math out there. We'll do more examples in class and hopefully help you feel more confident with this.